Okay, hello and welcome back. In this video, we're covering section 9.7 on an operation called the cross product. So we've been working with vectors in three-dimensional space, and this is an operation that applies specifically to 3D space between two three-dimensional vectors. So let's take a look at how it's defined, and we'll practice using it. So just looking at the given definition of the cross product, if we have two vectors and I can write it in component form as vector v being a1, b1, c1, so a three-dimensional vector, and vector w will be a2, b2, c2. We're told here that the cross product, which is written as v cross w, so like a big X, we can expand out using this formula, and it gets a little bit tricky. So take a look at what's combined in front of the I, j, and k unit vectors. So the first term will be b1c2 minus b2c1 times unit vector I. Then minus, so there's a minus in this formula, a1 times c2 minus a2 times c1 j plus a1 b2 minus a2 b1 k. So notice we get a vector as the result of the cross product. This makes it different from the dot product that gave us a scalar. We just got some value at the end. Here, when we cross two vectors, we get another vector, and we'll see how this new vector relates to the other two. In terms of trying to see some patterns in this, notice that this first term, this would be like the A term of our new vector. It involves B and C, so the components that are not A. In the B component of our new vector, it involves A and C, and we have the two pairings of those. So everything that's not B. And in the C component of the new vector, we have A and B paired, so everything that's not C. That can be helpful. We'll see another technique for producing this equation or this formula. But first, let's just work with it as it is, and we'll see a little bit on where it's coming from. So in example 1, we're given two vectors. Vector v is 2i plus 3j plus 5k. So I can say 2, 3, 5. And vector w is 1i plus 2j plus 3k. So let's use this formula in order to produce the cross product between v and w. And maybe it's helpful to label these. This would be our a1, b1, c1. And this will be our a2, b2, c2. So v cross w, the first term will be b1, c2 minus b2, c1. So that would be 3 times 3 minus 2 times 5. That would be our I term. Then minus a1c2 minus a2c1. So that will be 2, 3, 2 times 3 minus 1 times 5 plus a1b2 minus a2b1. So a1 is 2, b2 is 2, minus a2 is 1, b1 is 3. That will be for our k term. So that should give us 9 minus 10i minus 6 minus 5j It looks like I wrote a k here. It should be j plus 4 minus 3k. So that will give us negative 1i. So we can write negative I minus 1j plus 1k. So minus I minus j minus k. Or we can write it in component form as negative 1, negative 1, positive 1. So this formula can be pretty tricky to remember. Once we have it, it's easy enough to plug in. But we can actually produce this using determinants of matrices. So if you haven't worked with matrices before, maybe you have in a college algebra course, but if not, that's okay. We're just going to steal one operation, but we need to define what that is first, and that's called the determinant. So a matrix is a way of representing a collection of values, to put it simply in that way. Um, you usually see it represented using rows and columns. So we'll start first with a simple example, just a 2 by 2 matrix. So we can imagine the first row would be A1, B1. The second row would be A2, B2. So we have 2 columns and 2 rows, or 2 rows and 2 columns, a 2 by 2 matrix. And this operation called the determinant, taking the determinant of this matrix, we use these straight lines on either side. So that says we're taking a determinant. And to find this value, this is a value that we'll produce, we multiply the two diagonals, meaning I'm going to first look at this downward slanting diagonal, so starting with A1, and these will multiply. So that will be A1 times B2, and then we subtract the other diagonal multiplied, which is A2 times B1. So this gives us a value called the determinant of the matrix. And notice it looks like the same kind of style as we've seen um, in our formula. And that's no coincidence. So let's look at how this would apply to a 3 by 3, which we'll need since we are working with three-dimensional vectors. So if I do the same thing, now I'm going to have 3 rows. In the first row, we're actually going to place our I, j, and k unit vectors. And then the second row will be our first vector. We'll call that A1, B1, C1. And then our second row will be our second vector. So we can say A2, B2, C2. So to take this determinant, it's a little bit more involved. So we'll start first with looking at the column that contains the I, so this first column. If I were to cover up this column and look at what's left in terms of the bottom 2 rows, it produces this little box. It produces a 2 by 2 matrix on its own. We can view it that way. So the first step is to take the determinant of that remaining matrix. So I can say the determinant of B1, C1, and the second row would be B2, C2. So it's this remaining block. And this gets multiplied by the element in that first column. So the first element in the first column. So that's our unit vector I. Then we'll go down the columns and do the same thing. So what I mean by that is now I will think about covering up this second column and see what remains. I have these four terms, the A1, C1, A2, C2. So our second term will have a minus, because that we see that in our formula from earlier. And we can say the determinant of these remaining elements, so A1, C1 over A2, C2, and this will be multiplied by J. And then we'll do the same thing for the K column by imagine covering up this column. Then my remaining elements, which I'll take the determinant of, is A1, B1 over A2, B2. And that will be attached to the unit vector K. So let's expand now each of these smaller determinants. These are now 2 by 2 matrices, so we can do that like diagonal multiplication technique. So the first one would be this diagonal, B1 times C2, and then we'll subtract the other diagonal, which is B2 times C1. This will be attached to I. When we bring down this subtraction, now the determinant of this next one is A1 times C2 minus our other diagonal, which is A2 times C1. So that's attached to J. Then plus our third determinant will be A1, B2. This is like that one we did earlier. So A1 times B2 minus A2 times B1. And this actually produces the formula we were working with earlier. I can't get them both on the same page at the same time, but notice our first involves B and C, and the second term involves A and C, third term involves A and B. So this is our way of calculating the cross product between two vectors. We can say V cross W. So let's see some examples with some actual numbers that will help make this feel a bit more concrete. And it takes a little bit, when we're first using this, it takes a little bit to get used to it, but you should be able to pick up on the pattern after a few rounds of going through this cross product. So let's look at example 3. They give us two vectors and a few cross products to find. So I'm going to write out the two vectors in component form. They say that V is 2i plus 3j plus 5k, and W is 1i plus 2j plus 3k. So let's first find V cross W. These are actually the two vectors we were working with earlier, but let's see it using this matrix technique. So V cross W will be the determinant of the matrix that has I, j, k as the first row. The second row will be our first matrix, so 2, 3, 5. And the third row will be our second matrix, which is 1, or our second vector, which is 1, 2, 3. Don't want to mix up my terms there. All right, so let's expand this out. We'll write out each step this time, and then we'll be able to maybe jump 1 or 2 steps for our later ones. But first, we would have, covering up the I row, we have that bottom right square as our determinant that we'll find. So the determinant of 3, 5, 2, 3, that'll be multiplied by I. Then we'll have our minus. Then imagine covering up the J column. Then we'll have 2, 5, 1, 3 left over. Then plus, if we cover up the third column, we'll have 2, 3, 1, 2. 2, 3, 1, 2 attached to K. So let's actually evaluate these determinants. So that will give us, for our first one, so again, for each of these we're multiplying this downward diagonal and then we're subtracting the upward diagonal multiplied. So this should be 3 times 3 minus 2 times 5, I, minus, for our second one, we should get 2 times 3 minus 1 times 5, j, plus, for our third one, we should get 2 times 2 minus 1 times 3, k. So that will give us again our 9 minus 10, I, minus 6 minus 5, j, plus 4 minus 3k, or negative 1i minus 1j plus 1k. So we get the same result, but we have something more concrete, more of a procedure that we can replicate as opposed to just memorizing a formula. So that was V cross W. And part B, they ask us to cross W with V to do W cross V. We saw with the dot product that that operation was commutative, meaning that the order doesn't necessarily matter. V dot W is the same as W dot V. But is the same true for the cross product? Let's find out. If we flip the order in which we cross these two, do we get the same result? So let's express this as a matrix. I'll put I, J, K on the top. Then now the second row will be 1, 2, 3. So that's our W vector. And the third row will be 2, 3, 5. So let's try to jump to maybe this step without having to write out all the separate determinants. So we'll imagine covering up this first column. So then the first element should be 2 times 5, so 10, minus 3 times 3, so 10 minus 9, I. Then subtracting, imagining covering up our second column, we'll have 1 times 5, so 5, minus 2 times 3, so 5 minus 6, j, plus, now imagining covering up the third column, we should have 1 times 3, so 3, minus 2 times 2, so 3 minus 4, and that will be k. So let's just simplify everything. That'll give us positive I minus negative 1j, so that will become positive as well, so plus j, plus 3 minus 4 will give us negative 1, so we'll have minus k. So notice we get a different vector this time. So that means the property is not commutative, but notice we have essentially the opposite vector. Everything that's positive is negative, and everything that's negative is positive. So maybe we can say V cross W is equal to negative W cross V. Might not be safe to assume that's true based off of one example. Maybe we'd want to do more and even try to prove this just in the general sense. But this does happen to be true. If we flip the order of a cross product, we'll get a different, we'll get the opposite of our vector. So how about if we cross a vector with itself? Part C asks us to do V cross V. So what would happen here? V was the vector 2, 3, 5. So let's go through that same process. I'll have I, j, k. This will be 2, 3, 5, 2, 3, 5. So expanding this out, covering up that first column, we should have 3 times 5, which is 15. So doing this diagonal minus 3 times 5, we'll get the same thing. So minus 15, I. Then minus, covering up our second column, we would get 2 times 5 minus 2 times 5. So you can probably see where this is going. So 10 minus 10, j. Then covering up the third column, it would be 2 times 3 minus 2 times 3. So notice everything cancels. So 6 minus 6. Okay. So we get 0i minus 0j plus 0k. That gives us the 0 vector. The vector with 0 for all of its components. So if we cross a vector with itself, it just reduces to the 0 vector. That will be another property that we'll see. So let's look at a couple lists of properties of the cross product. The first one we just saw. So these are algebraic properties. The first one that we saw is that a vector crossed with itself gives you the 0 vector as the result. And then we also saw if we reverse the order of a cross product, u cross v, if we reverse it to v cross u, we get a negative version of the resulting vector. All of the signs will be flipped. The next property is about distribution of a scalar. So they are using alpha as some scalar, so just some number, not a vector. If we multiply a scalar by a cross product, it can distribute to the first term. So we have that scalar times u, and then you cross that result with v. Or you could also apply it to the second vector. So we could say the vector u crossed with the result of alpha times v. So we can apply it to either term and then cross that with the other vector. And then our last definition is you can view it as like a distributive property of the cross product. If we have u cross the sum of two vectors, so u is crossed with v plus w, we can express that as u cross v plus u cross w. So we can cross the vector on the outside separately with each vector on the inside and then add the results together. So it has a distribution property. There's also some geometric implications of the cross product as well. So one that is used a lot is the fact that the vector that we get after we cross two vectors, so we have vector u, vector v. If we do u cross v, we get another vector. That vector happens to be orthogonal to both u and v, meaning that it meets at a right angle with the other two vectors. Our second statement here is that we can describe the magnitude of u cross v as the magnitude of u times the magnitude of v times the sine of theta, where theta is the angle between our two vectors. Another one that we will use, so we'll work with this one with some examples, is that the magnitude of u cross v is the area of the parallelogram having u and v as adjacent sides. What this means is if we imagine some set of two vectors, let's call this vector u and this vector v, we could imagine some copies of these creating a parallelogram. And they're saying that the area of this parallelogram is equal to the magnitude of u cross v. So if we cross the two vectors, find the magnitude of the resulting vector, it is equal to this parallelogram's area. And then we get this last statement that u cross v is equal to 0 if u and v are parallel. So we get an interesting additional way to see if two vectors in 3D space are parallel to each other. So let's use this fact that the cross product of two vectors produces a third vector that is orthogonal to both of the original vectors. You might be asked to find a vector that has that property. So that's what we have here. We're given vector u is 3i minus 2j plus 1k, and vector v is negative 1i plus 3j minus 1k. And they're asking us to find a vector that is orthogonal to both of these. So that means we want to find the cross product between these two. So let's do u cross v. We'll use the matrix technique, so we'll have ijk, then our first vector 3, negative 2, 1, then our second vector negative 1, 3, negative 1. So our first term, covering up the first column, we should have negative 2 times negative 1 minus 3 times positive 1, I. Then covering up our second row, or our second column, we should have, and we'll have a minus here, so we'll have 3 times negative 1 minus negative 1 times positive 1. That will be our j term. And then covering up the k column, we'll have 3 times 3 minus negative 1 times negative 2. So let's simplify everything. That should give us positive 2 minus 3i minus negative 3 plus 1 j plus 9. Let's see. This will produce a positive 2, but then we will subtract. So 9 minus 2. That will be for our k term. So we should get negative 1i. This will give us negative 2, but then we'll apply this negative. So it will become positive 2, so plus 2j. And 9 minus 2 is 7, so plus 7k. So this vector should be orthogonal with our other two. Well, we can check this. If you remember from last time, we said that two vectors meet at a right angle, or they're orthogonal, if their dot product is equal to 0. So let's take this vector u dot v, or u cross v, which we just found, and dot it with our two vectors and see the result. So let's dot it with u. So if you remember that process, we will just, and I can write this in component form, this will be negative 1, 2, 7. We multiply each of the corresponding components and then add the result together. So I'll multiply the first terms together. This will be 3 times negative 1 plus the second terms multiplied, negative 2 times positive 2, plus the third terms multiplied, 1 times 7. So that will give us negative 3 minus 4 plus 7, which reduces to 0. That's negative 7 plus 7. So let's do the same thing with the second vector. So let's find u cross v dotted with v. So that would be -1 times -1 plus 3 times +2 plus -1 times +7. So that will give us +1 plus 6 minus 7, which also reduces to 0. So that tells us that these two vectors are orthogonal to the vector that we produced via the cross product. All right, our last example has us find the area of a parallelogram produced by a series of vertex points. So we said previously, and I'll copy it down here, that the magnitude of u cross v, magnitude of that resulting vector, is the area of the parallelogram with vector u and vector v as adjacent sides. So we're not given the vectors, but we are given the vertices of the parallelogram. So let me copy down our points here. We have point 1 is 0, 0, 0. Point 2 is 3, -2, 1. Point 3 is -1, 3, -1. And point 4 is 2, 1, 0. So the question becomes which sides do we choose? We need to imagine which sides will be adjacent, just to give a visual image. We have the four corners of some parallelogram. So let's just call this P1, P2, P3, and P4. It might not work out that way, but just to give some kind of visual representation. What we need to do is basically pick a corner and we can find the vectors between, say, like point 1 and point 3. We can find the vectors between point 1 and point 2. And then we can find the vector between point 1 and point 4. And what we want are the two vectors that are adjacent to each other. It may not work out that it's point 1 and point 3 and between point 1 and point 2. But if we find that one vector is a combination of the other two, if you remember, in adding two vectors together, say if we added the vector from point 1 to point 3 with the vector from point 1 to point 2, we would place the second vector on top of the first one. So that gives us the equivalent vector on this other side. And then we would say the sum of those two vectors starts at the beginning of the first vector and ends at the end of the second vector. So that would be the one going diagonal. So what that means is if we can describe one of our resulting vectors as the sum of the other two, that's the one that we would want to disregard, because that would be going across our parallelogram. And we're looking for two vectors that are adjacent to each other. So first, let's just find these three possible vectors. The one going from point 1 to point 2. We'll find the one going from point 1 to point 3. And the one going from point 1 to point 4. And if you remember, to find the vector going between 2 points, we would just take the difference of their corresponding components. So for each of these, since our first vector is the 0 vector, 0, 0, 0, or our first point, I'm sorry, is at the origin, 0, 0, 0. When we do the subtraction, we'll basically just get the second components. meaning the vector going from point 1 to point 2 should just be the vector 3, negative 2, 1, or 3i minus 2j plus 1k, because we're technically saying 3 minus 0, then negative 2 minus 0, and then 1 minus 0. So that means the vector from point 1 to point 3 should be negative 1, 3, negative 1. The one going from point 1 to point 4 should be 2, 1, 0. So the question is, are any of these the sum of the other two? Well, if I add the first vector with the second vector, we would add their components. So 3 minus 1 is 2, negative 2 plus 3 is positive 1, and 1 minus 1 is 0. So we can say that the vector from point 1 to point 4 is equal to our first one from point 1 to point 3 plus our second one from point 1 to point 2. So it is actually like our image that we drew. This would be like point 1, point 2, point 3, and point 4. And if we add these two vectors together, we get the one going diagonally through. So we want to disregard that third vector and just use the first two. Those will be our adjacent sides. So we just want to throw out the one that is a sum of the other two. So let's call u that first vector, the one that is 3, negative 2, positive 1. And then v will be our second vector, negative 1, 3, negative 1. So what we want is the magnitude of this cross product. Our area will be the magnitude of u cross v. So let's first find the cross product. We'll get a vector, and then we'll find the magnitude. So u cross v will have I, j, and k up top. Then our first vector, 3, negative 2, 1. Then our second, negative 1, 3, negative 1. So this should expand out. We cover up the first column. We will have negative 2 times negative 1, which will give us a positive 2 minus 3 times 1. So 2 minus 3, I, minus, covering up the second column and multiplying our diagonals, we should have 3 times negative 1, so negative 3, minus negative 1 times 1. So we'll be subtracting a negative, so that should actually become plus 1. Okay. Plus, covering up our third column and multiplying the diagonals, 3 times 3 is 9, minus negative 1 times negative 2 will give us a positive 2. So 9 minus 2. So that should give us negative 1i plus 2, okay, because we'll get negative 2 multiplied by a negative, then plus 7k. Oh, I wrote k twice again. This should be j. This will be k. So in component form, that would be negative 1, positive 2. I don't know why I wrote a 21 there. So negative 1, positive 2, positive 7. So that's our cross product, so let's find the magnitude. So the magnitude of u cross v will be equal to the square root of -1 squared plus 2 squared plus 7 squared. The magnitude of a 3D vector is the square root of the sum of the square of all of their components. So that should be the square root of +1 plus 4 plus 49. So that looks like the square root of 54. Well, root 54, we can write that as the square root of 9 times 6. 9 times 6 is 54, and the square root of 9 is 3, so that 3 can come out in front. So we get 3 root 6. This will be the area of our parallelogram. So just to review this process, I think the tricky part is at the beginning, especially if we're just given vertice points and not the two vectors directly. You want to pick a corner. This first point was perfect to pick because it was the 0 vector, but you might have a problem where it's not. So just pick one to be a corner point, and then find the vectors going from that point to the other 3 points. So that's what we did here. We found the vector from point 1 to point 2, and then the vector from point 1 to point 3, and the vector from point 1 to point 4. Once you have those three, compare them and see which one is a sum of the other two. So you should get that property if all of these are vertices of a parallelogram. So find the one that's the sum of the other two and then throw that one out. So that was our third vector. Then your remaining two will be the two vectors that you need. You can call those u and v. So we found their cross product and then found the magnitude of the cross product. And that gives us the area of that parallelogram formed by the 4 vertices. Okay, that'll be it for this section. So we found the cross product between two vectors. We saw some algebraic and geometric properties of the cross product. We saw that taking the cross product of two vectors gives us a third vector that's orthogonal to the original two. And we saw how the cross product is used to find the area of a parallelogram. Okay, that'll be it for this video, and I'll see you next time.